There we go. Okay, yeah, so this is the first of our monthly talks. It's meant to be fairly short talks. We want to just start conversations with people and hopefully excite you with the latest technology that we're working on. And so we thought that we would start with something that some of you might have already seen. We did publish at least I did one video, and then we did a promo video on the on this EM Inversion. So today I thought I would just replicate it a little bit, but push it a little bit further and try to do a constraint. So try to constrain frequency domain inversion model with for a time domain. So if you visit our YouTube channel, you'll see those videos, and then we'll add this one to the list after the talk. So the goal is really to just demonstrate how powerful it is if we start mixing open source technology with a free viewer like a Geoscience Analyst. And then this is really in line with what the UBC GIF group started doing a few years back with SimPEG under the vision of Doug Oldenburg, who most of you know. And so the idea is that if, as a community, if we can all have access to free and open source code, and we can just push the field a lot faster. And this is basically just exposing some of the code that already exists, and then I will show you where things are stored currently that you can view, you can modify, and hopefully collaborate with everyone. So yeah, so hopefully you see on my screen here, we simulated synthetic frequency and time domain data over the Flin Flon deposit. So we have like many other surfaces that describes this model, and here I'm only showing you the ore body. So we have a response on the time domain data, a very large response over the mineralization because we made it conductive. So in those previous videos, Carla showed you how to invert time domain data. Today I'll do the frequency inversion, and then use that model to constrain the time, as I said earlier. And then we'll just focus on line 10 here. So this is the model that if you watch this video, you'll see how to get there. Let's start from the beginning. So I'll just create a brand new project here. And then at the bottom of this video, once we upload it to YouTube, you'll get all these files. So you can rerun it on your own machine. So in the assets, I have two files, a VTEM survey and a DGM survey, and they're a GDB format, which is pretty standard. So I'm just going to slide those surveys in. So that's pretty simple. And I'm going to do the VTEM as well. Okay, so all it's doing here is assigning the XYZ coordinates and then the data. There we go. So now we have data in the camera. So we obviously made it easy. All the lines are overlapping on top of each other, so it's going to be much easier to constrain. All right, and so now let's just start an inversion right away. So in the list of files, we started adding some apps that basically those are just wrappers on top of technology that is open source, and we just make it easier for end users to just hit the ground running. So here I'm going to start a Jupyter notebook. I will do the tutorial number 4, which is the EM1B. Sorry, I need to do Jupyter notebook. EM1B inversion. Okay, and now we have this this app that shows in the browser. And basically all I'm going to do is save this, this project that I have now so that I can have the Python API to connect to it and access the data. So let me just save this project and call it my project. Okay, I'm going to copy the main here. Like this. Okay, and all I'll need to do in my notebook is I'm going to replace that file, and it's called my project. Like this. Okay, so right away, this little app here went inside. Let me do a side-by-side equal. Like this. So it went through my project tree here, and then found that I had like two line objects, and I'm going to start with the DGM. And then because on my DGM curves I have those channels here, the app recognized that it was a DGM system, and then assign all the frequencies accordingly. So I have the in phase 900, and I have 7200, 6000, which are like the usual frequencies for DGM. Okay. So here I'm just going to select one line, line 10 that we're talking about. Line 10 is here, and I'm just going to downsample this at 50 meters because you could do it full resolution, but I don't want to have to wait to make you guys wait for too long. And I'm just going to call this FEM. Make sure that everything is fine. Target misfit of 1. We're going to do a best fitting half space, and we're going to use the uncertainties that were pre-assigned. This is always something that user can change and test. Okay, I'm going to write the input and then invert. Good. So this is started. While this is running in the background, I will just, for those of you who are curious, that would like to see where things are, to see the backend code, everything is inside the functions. So those are the widgets, and the API, the current state of the Analyst API is going to be in the this Geo H5 IO folder, and this does all the interaction between Python and Analyst. So if you guys are curious, you can go look at the functions. SimPEG EM Wendy, we have a copy here. Anyway, all the widgets for these sliders and those windows are all here. So the code is completely open, and you guys are more than welcome to contact me later if you want to modify it, if you want to create something new. We can definitely do that. Everything is free to use. All right, so we're getting close to the result here. Just so that we can compare it, I will open another Geoscience Analyst project and just bring over that time domain model so that we can compare it. I'm going to open a recent like this, and I'm just going to grab this line. If you guys didn't know, you can copy objects from one project to the other by just Control-C and then Control-V in the project. Well, actually, this one is, the inversion is done, so I'm going to first reload my project so I can see the result. The result is here. Okay, my FEM inversion with all the iterations are here. So this is the FEM model, and I'm just going to paste the line here for the time domain inversion so we can compare the result. So here we're looking at the frequency. If I turn it off, this was the time domain result. So that's interesting, right? Because they basically both see the mineralization and they see some other conductors here. But notice that the frequency model has this layer of conductivity. I can just put it in log space; it'll be more obvious. Put this in log space like this. So the frequency system sees a layer here, and this is not surprising because FEM system like the DGM are really sensitive to the near surface because of the high frequency. If, for instance, if I just rerun this, the exact same line, but here I will turn off all the highest frequencies. So I'll turn off the 7256 for both the in-phase and the quadrature. And I'm going to just call this FEM 900 only, let's say, like this. And then if I run this, okay, first of all, you see that I have much fewer data points, right? I have only a third of it. And then once the result come out, you will see the difference. So basically, the 900 will be very insensitive to the top surface. So this is what I was going for today. Is since the frequency system sees parts that the time domain system doesn't see, we'll use this model here to constrain the time domain inversion. Okay. So let's just put this on the same log scale, just to prove it to you. So you see, we don't really have the top. And if I bring the ore body, the main ore body is this guy. You see that the time domain did a really good job at picking up the bottom ore shell, whereas the frequency system, I guess it did it okay, but we kind of have we start to get the Wendy effects here, where it doesn't really know where to put the response. Okay, so the 900 hertz inversion is completed, so I will refresh again my project. And now I have my 900 only here, and I'm just going to shoot the last iteration like this. So you see that we don't have as strong of a near conductor because we turned off the highest frequencies. That's an interesting thing to do, and with an app like this is that we can quickly test different scenarios, change uncertainties, turn frequencies on and off, and simply invert, and then get a sense of like where the signal comes from. Okay, so this is great. So what I will do here is I'm just going to say I'm just going to rename this file here. Sorry, not this file, but this model, and I'll call it let's say my best FEM model. Okay. So I'm going to save this like this. And now because I changed something in the analyst project, because we don't have a live link yet, I'm just going to refresh my notebook by reopening the project. Okay. And now I'm going to switch to the time domain inversion. Once again, because on my time domain system, I have channels called SF. This is standard for VTEM. VTEM always called it SF, the time data. So it detected it was a VTEM. Currently, we only have the 2007 waveform, but we can add more later. And I'm going to select line 10 as well. Downsample at 50. And all I'm going to do is use the frequency model, my best model, as a reference. So I'm just going to select model here, and I'm going to select my best FEM model. Okay. So I think everything is fine after this. All my time channels look all right. I'm going to write and invert. And this is going to be our last inversion for today. And hopefully you'll see how much it helps, how much combining both information from a frequency domain system and the time domain system can help. Maybe I can, while this is running, let's just start we can also add viewports here so I can compare my two models side by side. Okay. And then here I'm going to just show the, oh, I guess I am missing, I lost the time domain line, so I'm just going to bring it back again. Okay, so in this window, I'm going to show you the time domain model like this. And in this window, I'm going to show you the frequency. But I would like to see not only the 900, but all frequencies. My best model. Oh, everything is off. 1 second. Looks like I lost it. I apologize for that. It's because I reopened it at the same time in the notebook and here. So I'm just going to wait. We're gonna have a little Q&A session after this. So if you guys have questions, just prepare them and then we can discuss. I'm just gonna wait one more iteration. Okay, let's just refresh our project. Hang on, guys. Little technical difficulty here. Live demos are never easy. Oh, I have a question here from Diane. Diane is saying, bring it over. Are you saying that connective layers along the top is real or represent cover? I know that's not really relevant to you. Tell me later. Yeah, so because I tested it, right? This layer is real because I know the true model. And then if you remember, I showed you the difference between only the lowest frequencies and using all frequencies. And that layer disappears if you don't use the highest frequencies. I guess you have a point. It could just be an inversion artifact. But it's real in this case. Because I made a model. Okay, let me reopen my project. Hopefully we have it. And I guess we did not rename our model for the constraint inversion, so we're not seeing it. But there we go. So now what we're seeing here, I apologize for the little glitch earlier. I'm going to create again my viewport. Actually, let me bring back again this line. Okay, so now we have everything. So we have the time domain alone, right, with nothing. 1 second. Okay, this is the time domain inversion, just by itself. Okay, and I'm going to just add a viewport here, like this. And now on the second viewport, I'm going to show you what the frequency domain inversion look like. So here, I'm just going to turn this guy off and turn the frequency domain inversion alone. Okay, we have this. So this model, see the top conductor here, top layer, that's slightly conductive. Not as good as the resolution at depth of the ore body. You know, the third inversion we did is try to combine the best of both worlds. So try to use this model to constrain this guy. So I'm going to create another viewport. I'm going to put it at the end or in the middle. There we go. And in this viewport, this is the constraint model. I'm going to turn off this guy. So you can see we can have a hybrid between the two, right? And if I bring my ore body, like this, and I'm going to change this to connectivity to a log scale just for make it more obvious. So now you see that we gained that extra top layer here that came from the frequency inversion. So that's it. That's all I wanted to show today. Hopefully, you guys that kind of generate some ideas, things that we could develop. This is obviously just a prototype of an app. I try to do our best to streamline all the tasks, right? That you guys were most of the time getting bogged down on. For instance, setting channels, setting uncertainties, viewing things. So you saw that we could write an inversion fairly quickly, and then now we can start really like spending time asking real questions about geoscience. Okay, so if you guys want to, you can shout your questions if you have questions, or you can use the chat box to put something. That's it from me. Otherwise, I hope you enjoyed it. Okay, we have a question from Sean. Is there a way to review the misfit and predict that? Oh, that's great. Thank you. I completely forgot to do that. This is excellent. So let me just turn this off. And then let's look at the time, our last inversion, because it's the most, it's our best inversion, right? So here, let me just turn off everything else. This is fine, but turn off here. So we have our predicted data that sits right here, and it's a curve. And because it's a curve, we can profile it. So right here, I'm going to click on profile. So right now I have, this is my last iteration. This is the profile from the last iteration. Okay. Oh yeah, Chris is saying you can use the profile window, but I personally just use that one for now. And then if I add data, it's the residual, but I could look at the data itself. So now I have my observed versus predicted, and you can always scale these guys. Oops, lost it. Like this. All right. Well, we obviously, if you want to compare, you want to put them on the same scale. But then, so let's go 100 and 100. And maybe to make it easier, instead of using colors, let's just do blue and red. Blue and red. Bing. So now you see where you're fitting and where you're fitting less. Right? So it looks like we're kind of under fitting. Or which one is red? Yeah. So it looks like we're under fitting a little bit of the shoulder of the anomaly here. But overall, it's pretty close. This one is good. This one is good. You can also switch to residual because I exported it. So you see where the highest residuals are. So yeah, we're clearly underfitting this anomaly. I'm actually using, we are on the consulting side using the time domain, this 1D code to check for IP signal, because the negative time channels will always going to have a positive residual. So if you see any correlated positive, then you kind of have an understanding of where induced polarization could occur. Does that make sense, Sean? Excellent. Any other question? Okay, well, as I said, please feel free to email me. I will be posting this video with all the files that you need to run and some the installation batch file that you'll need to set things up at the bottom of the video later today. We got one more for Elisa. Marie said, "Hi, I'm here. Get a copy." Yeah, absolutely. Yeah, that's what I said. So I'll put a link at the bottom of the YouTube video. So our marketing department, Isabel, will pass it around to everybody who's on the mailing list, or you can just visit our YouTube channel tomorrow. It should be up. Does the Python notebook require a license for Geoscience ANALYST? No. So currently these two are very separate. So Geoscience Analyst can be downloaded directly from our website, the free version. So if you go to Mira Geoscience, I don't have it on my, if you go to our website, Mira Geoscience, or just Google it like I'll do right now. No. Anyways, if you go to our website, I have too many shortcuts. You'll be able to download Geoscience Analyst, okay? This is one thing. And then all the Python widgets and all the code and everything, this is going to be installed through Anaconda. So if you do a Google search for Anaconda, you want to be on Anaconda 3.7, install this guy, and then all the rest of the files will be below the video. Sounds good. Yeah. So the API currently is still under development. We haven't released it on PyPy or Anaconda or any of the distribution channels because we're still making sure that everything is stable, writing more documentation and everything. That being said, though, you'll have access to the current state of it. So if you want to start interacting with your project, you can use, you'll be able to use the current state of the API. It's just not very well documented right now, but if you're really itching to get started, contact me and then I'll get you set up. Okay, I think we're about 30 minutes in, so that's probably good enough to call it. Yeah, you're welcome, guys. I think the next meeting will be in a month from now, and then Chris Davis, my fellow colleague at Mira, will be showing different utilities within Geoscience Analyst. All right, sounds good. See you all. I'll end the meeting for all now. Have a good day. Stay safe. We can get through this. Bye-bye.